Okay, can you hear me well? Feel free to shout out any questions along the way here. We don't have to get all the way to the end of this sort of a thing. And I was asked 6 months ago or so by Inga to give one of these talks for the Saturday program, and actually I've never given one on sort of physics of the kind of research physics. I've given them here on things like the physics of music, which I don't do, but I learned about a little bit. And what I thought to do is think of a really pretentious title, because it sounded like a good idea 6 months ago, and then I ignored it entirely for about 5 months. And actually I had to give this talk in southern Indiana. There was a kind of a camp basically for charity, where they invited a lot of business leaders from the Indiana and Indianapolis area to this camp, and they donated during the course of this week $250,000. So I was I was like an activity. Like next to archery, they could pick archery, and they could pick like scuba diving, and they could pick talk to the nuclear physicist as an activity. So I went and I did this talk, and it was interesting how many questions you can get from lawyers and surgeons and so on. So along the way, I probably had 30 questions interrupting me, and it was really great fun. I may not be able to answer them all, but feel free to shout out whatever you'd like. Anyway, I called this thing the world's greatest scientific instruments, and then by that I already mean in physics, so I'm not going to get the biologists all upset and everything like that. And I'm going to tell you a little bit about kind of a swimming story about some things, starting off with some things I'm involved with just to set the scale for the really big things that I'm going to talk about toward the end. So for example, here's a little instrument. This is something I'm involved in a little bit now and for a while. This is a great big magnet, and we use this thing to measure some properties of the muon that were kind of interesting and still remain interesting, as Kevin mentioned. There is, in fact, a person right there. That's a man, and that's kind of a track which has a diameter of 14 meters. This is the experiment that our host Kevin works on. It's the CDF detector at Fermilab. It discovered the top quark with some of the people from Illinois leading the way before. And that's a great scientific instrument coming to its end in a few years. And this is an accelerator that's actually also complete now. This is an airport in Geneva, Switzerland. So it gives you the scale of this thing, sort of 30 kilometers around, underground like that. We'll come back to sort of this place later in the talk, but this particular instrument is, in fact, was finished some years ago. These are great scientific instruments, and they were the kinds of things that sort of push physics ahead in one way or another. Now, as a little preamble, people long ask sort of the questions, what's the world made of and what holds it together? And if you go way back, you'll hear these sort of answers like, they divided it, the air, earth, fire, and water, ancient sort of Greek style. And interestingly enough, I found this kind of remarkable, like little mathematical triangle-y kind of thing. Here we have air and fire, a little bit more organized than just those cartoon pictures. We've got hot and dry and cold and wet, and air is primarily wet and secondarily hot. So they were really, it wasn't just sort of making up 4 words here. They were really trying to categorize stuff. And that's stuff that we continue to do today. Humans try to characterize sort of what makes up the world and how the universe is put together and so on. And so we're going to give some more modern answers to that, or at least I'll give you the modern approaches to coming to those answers, if not those answers yet. So before we get going, I didn't know what Kevin would say, and I thought I would at least roughly introduce myself, which is to tell you one thing, is I was really not just part of this program in the Westinghouse Science. I dusted this off. This is actually my notes from my senior year in high school at the Westinghouse Science Honors Institute. It was a program like 200 years ago when I was there. And they gathered students from around the Pittsburgh area and brought us for these lectures. And I hated every one of them. And then there was a physics one, and in fact, it was low temperature condensed matter physics of all things, which I just loved. And that changed exactly everything I wanted to do. And if just in going to these sorts of things, somebody finds that, man, this is kind of interesting, we'll have succeeded in the way that things like that help young people all the time. I am a physics professor here. Nominally, my specialty is called nuclear physics, but I I sort of also do particle physics, and I suffer from this word a little bit because I realized, especially in Indiana, when they were going to like talk to the nuclear physicists, that they were going to, you know, not this nuclear physics and then not this nuclear, because I get that on the airplanes all the time. I'm dealing with that all the time. It's a burden I carry. Anyway, so what I actually do is what Kevin sort of mentioned. My group, which is sort of photoed here recently, we do these super high, ultra high precision measurements in physics, so kind of sub-part per million precision. So you want to measure something to the 6th decimal place or so, and you call on our little team to do it because that's kind of where we specialize in. We don't do a lot of those measurements. They take a long, long time to design and to do. And there's physics in that, and it's all historic. Many discoveries have been done just by doing very, very precise physics. But I'm not going to actually talk about what I do. I just going to segue from what I do into these things I thought were so interesting that I thought I would use the Saturday physics program and then this Indiana experience to learn about myself. So I'll be like your guided tour to Googling what are the great scientific instruments. Now, again, not so long ago, my group hit the big time. This is Time Magazine. Here we are, where the muon was, I like this, throws a 30-year-old theory of the universe into doubt. Not bad for a subatomic particle. This is my favorite little clip. You know, you get into Time Magazine, you're just a sentence, you're thinking, you know, you made it in life. The Time Magazine called the muon a winner, and, you know, I've probably lived off of that for a few years by now. And the reason for that was this little picture. This is a superconducting storage ring with a precision magnetic field of a 1 part per million uniformity, just an amazing uniformity. And in that, we basically put muons in and spin them around in a way. And this is the kind of data. It has this kind of wiggle stuff. And these wiggles go faster than what the theorists can predict. Okay, the theorists predict this very, very amazingly to a 0.5 part per million what this frequency ought to be, and this excites physicists like you wouldn't believe. So physicists get all crazy about this and write 1,000 papers or so about it, and that's kind of what we do. After that, it's its own talk, and I won't go into it. These days, my group summers in Switzerland. So here we are in Switzerland. This is the laboratory we work at right now, taking a reprieve from that other one, which was in Long Island, New York. It's not so pretty there. And here's the laboratory, and there are different kinds of multidisciplinary machines. Most of the work in this laboratory is actually condensed matter physics, but there's a machine in here, a little accelerator under there, that actually is the world's most powerful particle accelerator by energy. It's 2 megawatts of beam power, and if you go to the highest, it's not the highest energy, it's a fairly low energy particle accelerator, but there's so many particles in that beam that if you multiply the energy times the current, you actually come to 2 megawatts. It's an amazing thing. And we use that to do little things. This is an instrument that my group built entirely here. So all of this was done at Illinois, this little soccer ball here. And it's just an instrument to measure the muon decay very, very precisely, to measure its lifetime to a part in a million. And here it is getting on a hook to crane in. They crane it in, they crane it out every summer for us, and we use it for about 10 weeks, and then they crane it out and crane somebody else's apparatus in. This is small potato stuff. I'm going to show you some of how it works just in general, but this is tiny little things that a little group can build entirely still at a university. This is what it looks like when you wire it up. It's not so pretty anymore. It still has that soccer ball shape, but it's basically getting ready to have the beam stick the beam right into that thing, and it's on tracks and stuff like that. And it's ugly. Look at the rust on that and everything like that. We don't care about stuff like that. We just try to get the answers out by building the detector and doing it right. So here's the experiment in one animation. I'm going to show you one experiment that's extremely simple to show because it's just going to show a beam of particles come in. They stop basically on something that looks like a compact disc or a DVD. You think about exactly that size, exactly that thickness. It's a metal target or it's quartz or something, but it's exactly like that. And the beam is just a beam of very, very low energy muons. And muons are just electrons, but 200 times heavier. They're just special electrons. So they come in like this, boom, 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 boom. And as they get there, they're sort of the number that are there is increasing like this. But you see this turns over like when you charge a capacitor. But that's because some of them decayed. You see this one, it didn't last too long. So then we throw a switch. We turn that beam off with this fancy switch we built. And And then we watch these things decay. So we make a little radioactive source. We throw 20 muons in there. Then we turn it off. We watch them decay. We do it again and again. We do it until we get 10 to the 12th of these. 10 to the 12th of these. That's a big number. And that means for a little tiny tabletop experiment like this one, here it is with real data, little group like ours, we collect 65 terabytes of data. 65 terabytes, just a little group in a few weeks. So it goes wicked quick, and then we sit there for 2 years trying to figure out what we did. What it's about, it's the muon lifetime, it gives you something called the Fermi constant, S Fermi. The Fermi constant measures the strength of the weak interaction. There are 4 forces in nature that you're aware of: gravity, the weak electromagnetism, and the strong force. Gravity is, you can measure that with a pendulum. Strong forces are what binds the quarks together and holds protons together and so on. Electromagnetism is electric fields, magnetism, magnetic fields, and so on. And this is the weak thing which people usually associate with radioactive decay, things like that. It's a feeble little force, but it's one of the 4 things that you need to know. And people like Kevin know a tremendous amount about that, how it actually works, and probably uses this Fermi constant without thinking about it, because it's so very, very precisely known. So our efforts are little. That's our whole collaboration, or most of the ones that were available. And I remember the TV show where everybody knows your name. I think it was Cheers or something like that. You know, we actually do know each other's names, and we all work side by side, and that's the way that is. Now consider where I'm going with this. This is the Atlas collaboration for the new Large Hadron Collider. You're a part of this, aren't you, technically? Technically part of this group of people. Our host is one of the 2,000 or so people, of which there are probably no more than 700 or 800 photographed here at this very moment. This is a group photo of this particular pile of people, all working together to do one scientific experiment, to build one instrument. So instead of having 10 or 15 people, now the experiments have grown in size, and I want to tell you a little bit, you know, why. Now, the idea of, you know, little versus big, or cute versus monstrous, if you want, it can be a matter of style. You know, some people like to drive around that. It's kind of a cool thing to do. Somebody likes to drive around that. It's kind of a cool thing to do. And we self-pick where we're going in these things. I like to work in these little experiments because I can fiddle around and build the stuff myself and so on. And it can also be a matter of efficiency. I mean, some people like to fly from one place to another, 2 people in the plane or so. This is the new Airbus 380 or so. Obviously, you can haul a whole lot more people with that airplane than you can with the little. And sometimes it's a matter of power, you know, and sometimes there's a big aircraft carrier here, and size matters. And in these big experiments, it's not that Kevin really doesn't want to work with his little group at Illinois only and maybe one other group from some other institution. Size matters. 2,000 people or so, it may take 2,000 people to build this gigantic device, as you will see, just to pull off the physics. It's so much more complicated than the little things I'm talking about that I do. And then I was thinking about, well, in this pretentious title of mine, what does the word world's greatest mean? You know, so here's the acknowledged world's greatest basketball player, Michael Jordan. You know, he's on the Wheaties box, so you know it. And everybody realizes once a year they have to get this thing for the world's greatest mom. I mean, probably some world's greatest moms are in the audience today. And then I was thinking, well, as I kept looking around, here's the world's greatest tow truck I found on the web. I mean, and it goes like that in life. And, you know, for physicists, there's the world's greatest scientist, and this is Einstein. And we don't even argue that too much, I would say. It's not hard to do. But then you start thinking about what are the world's greatest, like, achievements, instruments, things that mankind has built outside of physics. And it's not hard to get these things because they're listed for you. You know that there are sort of the 7 great wonders of the ancient world, of which there is only one left, actually, interestingly enough. The other 6 have long been destroyed, earthquaked, fire, burned, and whatnot. That's why they want a new list. So you may be aware that there's this kind of interesting worldwide poll going on about what are the great wonders of the world now, you know, and it's going on and on. But what's left is the Great Pyramids here. In fact, when I thought about the title of the talk, I was really thinking, what are the pyramids that scientists are building today, collectively? Because a little group from Illinois didn't decide to build a pyramid. but probably a few thousand people over a long bit of time had to build that pyramid. And that's the kind of instruments we're talking about. And, of course, here's the Golden Gate Bridge. So this is one of the acknowledged new 7 modern wonders of the world. And they're sort of voting still, so I can't give you where it is. Now, if you want world's greatest things for physics instruments, people don't just go and build great instruments for no reason at all. They build great scientific instruments because somebody has asked a very great and acknowledged scientific question. Somebody has asked a deep, penetrating, fundamental question about nature for which the instrument is being built to help answer that question. So there I needed some guidance. So I went to some of the kinds of questions that people write down right now, and you can find these in many surveys around the world from all kinds of physics communities that think about these things. And you've got questions like, what is the universe made of? Why is the universe made of matter? This is one of my favorite ones, and certainly one of Kevin's favorite ones for all of his career. Why are we here? What we write down in the physics laws that we know today cannot explain at all why we are here. If you acknowledge that there was a Big Bang, and all of a sudden, forget what happened before the Big Bang and all kinds of other things, but let's just start like way back there at least. At one moment, the universe was equally full of matter and antimatter. But we're not made out of antimatter. We're all made out of matter, and everything we see is made out of matter, and the antimatter has sort of secretly disappeared. And people like Kevin have chased down avenues of why it may have disappeared, and they can certainly see ways that it does disappear, but he can't come up with enough. So Kevin, total failure. Didn't come up with enough. And the answer is, still we don't have the answer. We have to figure out why we ended up here. We know there's physics beyond the standard model for the simplest answer of all, because we're actually here to ask the question. Now, what gives particle their mass? This famous book by The God Particle by Letterman, right? These guys, with their high-energy physics machines up at Fermilab and other places in the world, they hunt for this thing they call the Higgs particle. You've probably heard this word, the Higgs particle. I don't have any idea what this Higgs particle is. I just know they've been hunting for the darn thing for an awful darn long time and spending a lot of money doing it. This is the thing. This is a particle, though, that in sort of the sort of theoretical way of thinking about physics gives the particles that we know, gives us mass. Gives us mass as you drive through this field, this Higgs field. And they know they can find this Higgs field. And it's pretty important that we find this, because otherwise it's going to way throw off our understanding of particle physics. It's necessary. It's a necessary evil. It starts us off. It finishes, in some sense, it finishes, it's probably the last nugget of really basic standard model physics that has yet to be found, so we can go on. Outside of particle physics, in a way, what is the nature of some of the violent interactions in the cosmos? Black holes, supernovas, gamma ray bursts. What's going on out in the universe that's created, you know, we have, in the second question as well, what is dark matter and dark energy? I mean, you will get some talks, I think, on that. But we now know, and we know this very precisely in the last few years, we know that of all the universe that we study, kind of like the matter, the stuff here, and beams and whatnot, that's like 5% of the universe. So we got like a lot of work to do. 95% is out there, and it's in dark energy and it's in dark matter. Dark energy helps sort of the expansions of the universe, and dark matter is sort of this feeble stuff that we don't know what it is, and lots of theories, lots of connections. One of the connections of interest to me is that the reason our little Time magazine article maybe says that something was wrong with the wiggles in our experiment is some people think, aha, we were sensitive to the dark matter. The dark matter could actually be something that changed the frequency of the spinning of our muon. But that's, you know, a pile of theorists buy into that, but a pile don't. And we have to do some real experiments to figure it out. So these are the kinds of big questions that drive research. There's more. You could make a longer list. These are some quick ones I could come to articulate for you. But here's a little history of the universe. It's a cute plot that you can get online from Berkeley Laboratory. The instruments I'm talking about are going to take a look. Here we are now. Like, this is me somewhere out here giving a Saturday physics talk. And, you know, you go back in time. This is a time axis. Here's the Big Bang. And we're looking at sort of tens of microseconds after the Big Bang. You can peek back to that era because it's at that era where these things that I'm talking about changed, where the asymmetry changed so that we have matter, not antimatter, where the soup that I'll talk about called the quark-gluon plasma sort of emerged into real particles and so on. So it's back there. Now, lots of times I go to some of these kind of particle physics-y talks that are in outreach, and people start going down the alphabet soup of particles. Well, this is your basic periodic table. You've probably all seen these charts in books in chemistry and so on. Then this is your basic atom. It has electrons swirling around the nucleus here, a nucleus made of neutrons and protons. And then kind of this is the modern kind of periodic table of the elementary particles that you often see. These are quarks. There's 6 quark names, and these are leptons. We're all made out of up and down quarks, basically. That's the protons, surrounded by electrons. And the one I was talking about, and here's the electron, I mentioned the muon numerous times. It's just in a different category, a family there. But in fact, I didn't want to talk about these things at all. We could go on and on and on. I could spend the next kind of hour or so giving you all kinds of stuff that you may or may not remember, tomorrow on that. But let's not do that. Let's just assume that somebody else will give that talk and tell you all the alphabet soup about particles and blah, blah, blah. And, instead, let me stop for a moment and show you a little bit about how people build instruments to see these things, because you can't see these things. They're too small, they're too fast, and so on. Well, let's just start with a source. I don't have a big particle physics beam in this room like we go to accelerators because we have nice controlled beams, but it doesn't matter because we're getting rained down right now by particles from outside the Earth, and these are cosmic rays. So cosmic rays, here's a proton which just comes streaming through the cosmos, and this is Earth, and it will hit here, has quite a range of energies. That means basically speeds. Think of this cosmic rays having a fast or slow or so speed, if you will. Here's a zoom-in picture. It hits the atmosphere, and bang, it splatters, what we call shower. It really splatters by hitting the atmosphere, this high-energy collision, and busting into lots and lots of other so-called secondary particles. And we get rained down on those by particles, one of which is the muon, my very favorite particle, as you all should know by now, which is my favorite particle. It's a big quiz. And we're getting hit by these things at the rate of something like 200 muons per square meter per second. So that's kind of on this table here. On this table, looks like it's about 2 square meters, so a few hundred muons might be hitting that just as we, every second, every click. This is actually a fairly typical thing that's in most upper-level universities. This is, in fact, at the University of Illinois, something that I built a couple of years ago for a class, just a class. And this thing catches cosmic rays. So the detectors that I'll show you here are employed to do this. And a cosmic ray will come down here and stop in here. If it's a muon, this is a measurement by students, really just basic undergraduate students who aren't specialists in this. They have no more than 2 weeks to work on this experiment, build it, and so on to do it. And here's a very good measurement, actually, the muon lifetime. Interestingly enough, it's essentially competitive with the first ones that were done in 1959 with beams when it was really discovered to do this. It's pretty accurate stuff. But how does it work? I've got some detectors down here that I want to explain. They're all flashing up there and over here in the photograph, and I'm going to walk around in a moment. But I want to tell you basically about the basic elements that make up these instruments. And what I hope to convey to you is that even though we have these little things here, we use them in our laboratories for the students. I use them in my little tinker toy experiments that I do in Switzerland. I'm going to basically tell you that Kevin still needs the same darn things when he builds this giant thing with 2,000 people and sticks it underground and runs it for 20 years. It's the same basic stuff. So let's take a look at that. Here's what's called a scintillator. You can see this thing glowing here. It's not just a piece of plastic there. I drew it blue like that. It's got a photomultiplier tube on the end of it. That's something like, well, they're in here, and here's a big one, which I'll explain a little bit more about in a bit. You can see this thing glowing blue when it's hit by a black light. If this was a piece of plastic, just regular plastic, it wouldn't really glow blue. This is regular plastic here. So this blue is because this plastic has been doped with a fluorescent dye. And when the particle goes through that thing like this, bang, you get a little pulse on the oscilloscope. And that's actually what you're seeing right here. So over here in the little setup that I made, I have basically one of those, it has to be wrapped because you sure don't want to hit this photomultiplier tube with outside light. So it has to be completely dark, which is why you see this thing is black. So in this object here is just a piece of that blue stuff, and then the connection from the end of that blue stuff to this photomultiplier tube is just clear plastic. It's called a light guide. That just channels that light on over. And I've got one here on the top and one here on the bottom. Just for the moment, all you see, every time the oscilloscope flashes, wow, that's a big one. There we go. The blue and this yellow trace right here are flashing together because a cosmic ray is going through there every time they flash. So I can kind of, this is dangerous and you don't want to do it at home, but you can put your hand under that. You know, you're getting hit by them right now. Safe again. It's somewhat dangerous to fly in airplanes a lot because in airplanes you actually get hit by quite a bit more. You know, you're up there. Down here you're shielded a good bit. If you really want to be shielded, some of the experiments have to go deep underground. I'll show you one that's deep underground just to get away from being rained down by those particles. I have another detector that's in between those scintillators, those plastic scintillators. It's this bar here, which I got from Matt Sellen. Matt's has given this talk before, kind of a talk like this. This is a great idea. This is called a so-called shrink-off detector. And you might be used to the idea of an airplane that flies faster than the speed of sound, and it makes a what? Sonic boom, right? Big shock wave behind it. Or a boat which goes along through water fairly fast, leaves a bow behind it. So imagine, okay, what by now people have taught you, Einstein, our famous physicist and everything, taught you, can anything go faster than the speed of light? No. But how fast do you think some of these particles can go? Pretty wicked fast, right? Like 0.999 of the speed of light. So they can go close to it. So suppose you're a particle and somebody's built you a nice accelerator and you're very happy because you're going 99% of the speed of light and you suddenly go splat into, well, let's just say you go through this. You just go through that. Well, you don't suddenly brake and slow down a little bit and then speed up again. You go right through that at 99% of the speed of light. You don't slow down. Now, how fast is the speed of light? What do we know about the speed of light? It's constant in vacuum. But the speed of light in material, is it the same? It's not, right? Otherwise your eyeglasses wouldn't work and all kinds of stuff. So it refracts. It goes a different speed by something called the index of refraction. So in fact, the speed of light in this material is like 30% slower. Or in water, it's about 30% slower. It's typically like that. So this particle goes through that piece of plastic or through a bucket of water, which I'll show you next, or through a piece of quartz, which is what's over here in that setup, faster than the speed of light goes through that material. Not faster than the speed of light, but faster than the speed of light goes through that material. It makes a shock wave, just like that, a light wave. And it's actually directional. So it's not just that it lights up. This shock wave can be seen in this direction. It's kind of important for a couple of the big instruments I'm going to show you that phenomena works. And so what you're seeing here in this object right here, I'll pass it around in a moment. This is a beautiful, beautiful polished piece of quartz with two photomultiplier tubes at each end. It has these little, they're here, the purple and the green. So when the oscilloscope fires, when the top counter and the bottom counter each see something, and you'll see that the green and the purple one very, very often fire at the same time because something's gone through it at the right speed. It has to go, it's not just anything, but it has to go just at the right speed. And that's a pretty cool detector type as well. So we have two detector types right there. Then there's this is a piano. This is not a particle physics detector. It's actually a piano. And, but it's a very good analogy to what I'm going to show you next. Suppose a cosmic ray went through a piano. Okay, if it went right through a piano, all of a sudden, again, imagine if that string of the piano went ding just as it went by. Well, particle physicists made detectors with basically this kind of idea. They're called wire chambers, multi-wire proportional chambers or drift chambers, and a whole series of chambers. Even led to like the Nobel Prize for this kind of device not so many years ago. This is one that's all wrapped up into a cylinder. They can make them in planes. They can make them in any shape you want. And instead of it making a sound, this area between the wires, and they really are wires, thin tungsten wires with high tension, they're put at very high voltages. There's just electric fields between those wires, and there's certain kinds of gases in there. So they basically make an ionization and make an electrical pulse on that wire. That tells us where particles are. Lots and lots of these tell us which way they go. So you can image. Now we know that particles fire. We know they have certain velocities. We know what tracks they go on. And sometimes we need to know what energy they have. And there's a class of detectors called calorimeters, from that word calorie that we're all kind of worried about these days. Calorie is related to energy. And so this is a big device. There's a guy, just to point out what Paul said, this is a person standing inside a gigantic detector. And the idea of these detectors is when a particle goes in to just absorb all of its energy like, whoa, and then give out some kind of a signal which is proportional to that. And I've built a bunch of those in my life. Mine are all little. Remember, everything I do is little. Here's one. You could pass this around, even though it's made out of lead and scintillating fibers. I have it, don't worry about the lead because it's all wrapped up and there's sort of a shellac over this. So you can, I mean, I don't want to do that. But you can look through this on if you've got a little something, just look through to read something on that. And I'll shoot that your way and just zoom it up there and then zoom it down there and the last person can fling it at me. Down here, I have bigger versions of those. This is kind of the brick that we make. We made all these at Illinois. We have a little factory that weaves all this stuff. This is the letter I back here. I think you see the shadow of the letter I here. These are fibers, and these are getting seriously heavy. Detectors that are calorimeters are very heavy. That kind of thing, I wouldn't even venture to guess how many tons that is. Maybe Kevin has some idea. 1,000 tons. It's very heavy, typically made out of lead or tungsten or some other material that's very, very heavy metal. And in between, some kind of an active detector. It could be a scintillator. By the way, the fibers that are in there, the little fibers, are exactly made out of this stuff. We're back to this again. They don't do much to stop the particle. They just tell us what was going on at the time. Okay, so you've seen some of these different detectors. Here's me actually. That's actually me as a graduate student. A long time ago in 1984, when I was a graduate student, I was a helper on this experiment. I was just a young student that carried cables and did some of the computing for the thesis of somebody else. This is actually a bucket of water. I could draw it like that, but it's much better to have the photograph so you can see that it is, in fact, a bucket of water. Now, this bucket of water has two of these so-called photomultiplier tubes, one on this end, one on that end. They're each about this big, like that, a little different shape. These come in all kinds of shapes. So it's plop, plop, like that. And the guy in our group, he spent probably 2 years building this bucket of water, which makes you think he was taking a lot of, Starbucks time before Starbucks was invented. But in fact, it's kind of a special bucket of water. It has all kinds of goop in it and so on, and it had to be very uniform. But with that was the last time the muon lifetime was measured, the most precise measurement, and it held for 20-some years until our group beat it this summer with something. This is a really simple experiment. You brought in a beam of pions, call them muons if you want. They stop in the middle, and when the muon decayed to an electron, the electron went faster than the speed of light in the water and made a light burst like that. And we just did that a lot of times in a row, and you end up with a nice thing. We laughed at this, the two of us. This is another graduate student. We laughed because I think it wasn't so impressive of a detector. But the idea was there. And now I want to extrapolate to the big things. Imagine a bucket of water 100,000 times larger than what I just showed you. 100,000 times larger. This bucket of water exists in a mine in Japan Why is it in a mine? Why is it deep underground? To get rid of all those cosmic rays, mountain over top of it so it just shields them out, so that kind of like a calorimeter just absorbs those cosmic rays and makes them pretty much disappear. How big is this thing? Well, 40 meters high. Think of football fields. I always like to think of the 40-meter thing that they make football players run. I don't know why they don't make them run the whole 100 yards. If you're a running back, you've got to run 40 meters, but then you just get tackled, I think. And 40 meters across, and it has some 11,000 or so, 13,000 of these things, except not like this, way bigger like that, like huge ones. They were $12 million worth. I don't know how many $1 million worth. It was an enormous thing. And there was actually an accident not so many years ago where there was a kind of a mechanical shock wave in that big tank, and they all broke. Like 90% of them just crashed because there's a vacuum inside of here. It was an incredibly expensive thing and a very sad day for physics, actually. So this detector, I'll explain in a minute what the physics of it is. But the principle is essentially the same idea of this Trenkov counter here, of this bucket of water that we used. It's just a great big bucket of water. Now, here's some things about neutrinos. Neutrinos have been very popular in the last few years or so because there's been a real revolution in physics in the area of neutrinos. So our sun, look up at the sun, don't really look straight at it, of course. Our sun produces a tremendous amount of neutrinos because, in fact, it is a nuclear physics factory. It is a nuclear power plant. And all nuclear reactions, they go by weak decays and weak interactions, and they are, in fact, emitting neutrinos constantly. So that's a huge source of neutrinos right there. The Big Bang, that was a long time ago, 13 billion years ago or so, actually left a lot of neutrinos, remnant neutrinos, flying all over the universe, 300 or so that are per cubic centimeter. All the power reactors, Clinton reactor and everywhere else, makes lots of neutrinos in all of the production of energy they do. Neutrinos are really harmless. So if I scare you, do not be scared. They just go right flying through you. They won't interact. And they're very, very hard to detect. So in order to detect one, to catch one, you can't use like a little detector like I like to build, because you never, ever, 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 ever would get one. So you have to build a detector, 100,000 times bigger than the ones that I showed you. And there they only catch them very, very rarely as well. And how they catch them is that the neutrino goes into that water and bangs onto something in the water, and it's something in the water that gets banged that then lights up the Cherenkov light, and then they go, woo, we got the event. So here's a neat thing. How feeble are they? Suppose you took the entire space between the Earth and the Sun. Here's the Sun. Here's the Earth. The Sun is producing a lot of neutrinos. And suppose you filled it with lead, solid lead as a shielding. That would be a lot of shielding. Only one in 10,000 of those neutrinos would even give a hoot. If that gives you an idea of how hard it is to catch one. They just do not interact. They call it a cross-section for interactions very, very low. This is that detector kind of in a more schematic view under this Mount Ikeno in Japan. These are sort of tunnel systems and so on. It gives you a little bit of the idea. There's control rooms and so on. This is the wall of photomultiplier tubes. This is a great picture to give you a perspective. If you're in there doing maintenance in that, this is water. These are guys, like 3 or 4 guys, technicians on a boat. And on a boat inside the detector, okay? They are riding around in the inside of the water tank. These are all photomultiplier tubes, and they're riding around one by one, sort of tuning something or changing the electronics or whatever they're doing. Of course, the water is going up to the top. I don't know how they get out in the end. But here's another perspective of those things. So these little dots are all the phototubes. So what did it do? Mats gave a lovely talk on this some years ago at a Saturday thing. So I'm just going to give you a 1 or 2 minute clip of Mats's conclusion. But I'm not going to tell you about this thing and not tell you any physics of it. They really measured this Nobel Prize, which is related to the fact that it proves that neutrinos have mass and that they flip-flop into different types. So here we have the cosmic ray I showed you before. It splatters on the atmosphere, a splat. It makes some muons, and some of those decay, and in that decay are some neutrinos. So there's the neutrinos, and those are a muon neutrino, and it goes. And here's the detector, and it's conveniently painted under the surface of the Earth. So it gives you the cartoon. And here is a big view, stepping back. That's the detector under the surface of the Earth getting whacked. So the cosmic rays, imagine if you looked at the direction. And they can look, in this kind of experiment, they can figure out which way it came. That's part of the idea of all those instruments. Which way did it come? So suppose you counted how many came there, how many there, how many there, there, and there. You figured it out. And then you made a plot from the top to the bottom. Here's the Earth again. Here's the plot. This is what you would expect, and this was the data. So from the top, you get the expectation is right. From the bottom, the expectation and the data are different, a lot different, statistically very different. So what that means is that these kind of neutrinos that you were sensitive to, which got produced, always produced right here on the edge of the red, this orange or whatever color it is, they got made just above the surface of the Earth by the atmosphere. That's where they got born. And here they only had to go from the surface there to the little purple box, not so far, a few hundred meters or so. And here they had to go from the surface of the Earth, the surface where they got made. Then they had to plow all the way through the Earth and get to the detector. Now, these guys are smart. They can calculate how far away that is and so on. It isn't that effect that you're looking at. But what happened is along the way they changed type. They just, whoop. Imagine if you could change into your brother or your sister along the way and somebody was looking for guys and a girl showed up. Something like that. And that's what happens, except there's three of them. There's three of them switching who they are and what they are. And this resolved a puzzle which was for 40 years standing puzzle, more or less, in the physics of the sun and the physics of neutrinos. And proved that they really, all the textbooks have now had to be rewritten because everything I learned in the textbook said this wouldn't happen. So Kevin and I, we learned blah, 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 neutrinos have no mass, there's three types, blah, blah, blah. That's all wrong, all in the last few years. So we have to be prepared, as physicists, scientists, we have to be prepared to throw away old textbooks. Here's another thing. This is a picture of the sun, a photograph of the sun from that neutrino detector underground. This is a photograph of the directions of the neutrinos. So imagine this box of water underground in a mine can point back and see where the sun is. That's pretty cool. A photo of the neutrinos from the sun. Here's another thing coming up. They are building, here's Japan, okay, here's some mountains. This is the curvature of the Earth. And this distance from here over to here is about 300 kilometers, okay, a couple hundred miles. They are building right now as we speak a roughly $2 billion particle accelerator right here. It has a lot of purposes, lots of things that people will do with that particle accelerator. But the first experiment, one of the most marquee experiments, will be to shoot an artificial and very directed beam, like a laser beam, of neutrinos at that detector there. Now, to get it, of course, neutrinos aren't going to bend like the surface of the Earth. So you actually have to calculate the angle right. You need engineers and everything here. You have to shoot the beam underground, knowing that it's going to pop out and whack into the detector under the mine over here. That will very, very precisely measure some of these parameters of neutrino properties. And people in the physics community are really looking forward to this. This is a big deal thing. So this experiment with the bucket of water or so continues to be really, really an interesting scientific instrument. Probably more prizes are coming. Here's something that I found just spectacular. So, cosmic rays, I mentioned them. We've been watching them go through. I let a few go through my hand. The highest energy proton ever recorded in the history of big detectors has an energy of something like 3 times 10 to the 20th electron volts. So that means it shouldn't mean anything to you. It means absolutely nothing to me unless I sit down and kind of calculate what that means. So here's some things that people have written down that have 3 times 10 to the 20th electron volts of energy. A Tiger Woods tee shot. So imagine the energy associated with an entire golf ball flying at a Tiger Woods kind of speed, all concentrated not on the Avogadro's number of protons or so that are in a Tiger Woods golf ball, but all on one proton. That one proton carrying that much energy. If that hit you, woo! You know, you got smacked by that. Roger Clemens fastball or a tennis serve or so, all in one proton. So some physicists are curious where in the cosmos are the things that accelerate a particle like that. And frankly, we cannot come up with that very well. We can see that they arrive, they hit the Earth very rarely. But if you look through sort of the physics of what we know in the astrophysics, we don't know really the mechanism. There's some sort of speculative things. but we don't really know where they come from. So how would you catch some more of those to find directions? How would you do something to, this is just one. How would you get an instrument which could catch these things? Now, you should probably already guess that this has to be pretty big because it has to absorb a lot of energy, right? How about this big? This instrument is 20,000 times larger than the big bucket of water underground in Japan, which I called Super K. So first I started with a bucket of water that I was used to using as a student. Then I went 100,000 times bigger to that experiment, now 20,000 times bigger again. This is the Eiffel Tower right here. This is the experiment. To make a big bucket of water that big, there are two ways people are doing it. In Antarctica, you can use the ice. Old ice, it's extremely clear. It's just water after all, so you get the exact same thing. And also in the Mediterranean, deep under the Mediterranean Sea, there's an experiment called Antares, I believe it is. It's the same sort of idea. And you're not going to be able to make an artificial tank of this, so you go someplace where you have nice, clear water. But let's take a look at this one. This is being built by the National Science Foundation and many institutions around the world. It's very difficult to get to. It's a cool thing. And how does it work? Well, the same idea. Photomultiplier tubes, looking at the ice, looking for the shrink-off effect. Everything else is engineering, digitizing them, making them get their signals up to the surface of the Earth, having the physicists that do the work actually figure out the patterns of the way the lights went off, so and from those patterns they can calculate exactly what happened. So where is that? Here's a trip to the South Pole, and this is actually where it is. The National Science Foundation runs a scientific station at the South Pole. There's no penguins here. Remember, they're on the edge. This is a runway. This is the whole scientific complex. This is the profile of the size of the detector. Of course, it's under the ice. They bring every single thing in. Is very difficult. They can only work for a few months a year. In the winter time, roughly from November to February or so of our time is their summer. So that's their summer. They bring everything in on these big sled dogs here. And this is them drilling. They drill through the ice with this kind of hot water jets, 5,000 gallons per minute. So the people that are really down there are typically miners and drillers. The physicists are all up having lattes in Wisconsin, basically, at the Institute doing simulations of the physics. And a couple physicists go down there to say they did it and tough it out. But most of them are doing this kind of thing, which is a simulation. All of these are strings of these photomultiplier tubes, and these are the patterns that would find for an event which would be a neutrino event coming from all the way through the Earth, which shields everything else. So they actually look, okay, you put them in the ground. Imagine if you're in Antarctica, you put them in looking down like that, which means, turn the Earth over, they're looking up at us. Those phototubes are looking up at us. They only want stuff that's been shielded from the Earth. Pretty cool. It doesn't matter. No, nothing with gravity. It doesn't really particularly, I think, matter that it's there, except that this is a real nice place where there's been a scientific station for a long time. So the infrastructure is there in the ice. And maybe they put it in the middle because since global warming is melting, it'll last a little longer if it's there. You know, the edges will go away. But the neutrinos are just not going to be affected at all by gravity. They're not going to be affected by any of the magnetic fields around the Earth, any electrical fields, or any. They just don't care about anything. They just go. This is another instrument that looks back in time. This is the Relativistic Heavy Ion Collider. It's actually operating right now at Brookhaven National Laboratory. My little experiment, by the way, was at Brookhaven as well, in this little area here. Everything I do is tiny compared to what people really do. So the experiments there, they're two big experiments, one called STAR and Phoenix. We have some people involved in this one at Illinois. And what they do there is, again, look at this soup of particles before they sort of formed into matter the way we know it now, meaning matter that glumped together into things like protons and neutrons. When it was all freely swimming around, it was a soup, and they called this soup something like the quark gluon plasma. And people were after trying to create this sort of soup really close to the Big Bang. And when this instrument first came on, there were a lot of people in the world waiting for the first collisions of gold hitting gold at such a high energy they were afraid that we were going to make a new Big Bang. And so they had to get serious physicists to write papers to try to calm the public down that as soon as we turned the machine on, we wouldn't boom and blow up and create a brand new universe. So it was a scary moment for some people. Anyway, we didn't. This is kind of cool. What they do is they take lead and hit lead or gold and hit gold at very, very high speeds. So imagine if you had, let's say, think of billiards for a moment, and suppose you had a few hundred billiard balls sitting there in a rack and you were going to hit it. You might hit it with a proton. That would be one kind of a collision where you take a nucleus and you hit it with a proton and they would scatter. We learned a lot of physics from that. Now imagine if you had a few hundred billiard balls in a rack and then you hit it with a few hundred billiard balls when you cued it, boom, until they went like that. When I was taking nuclear physics as a graduate student, I had a teacher who didn't like this emerging field, like he hated it. Like, in fact, many, many physicists hated the idea of this. They said, oh, it's like trying to learn, you know, how a Swiss watch works by throwing a Swiss watch against a wall. You know, busts and springs and so on. You'll never learn anything, blah, blah, blah. I had that drilled into my head. I would even say half of the nuclear faculty around here had that feeling. I did not. I felt this was, come on, give me a break. Here's a picture. This is a very correct animation of these two lead nuclei hitting each other at pretty high speeds. Let's see if I can, I might have to hit a mouse on this one. Doof. Sparklacko. Now, you've got to build a detector around that thing and catch every one of these. What was the particle? What color was it? Maybe, which was what type of particle? How fast was it? What distribution? And from that, you can recreate statistically what was going on in these few microseconds after the Big Bang. What were the forces of nature that allowed sort of things to bind and so on. And we learned a lot. This is actually a detector, the star detector. This is one single event. These are all tracks of the particles. This detector is so amazingly good at visualizing where everything came from that I just showed you that you get these spectacular pictures of these collisions. And what they basically learned, without going into this in detail, this is a diagram of the density of matter here, and the temperature is kind of how kinetic it is, how much energy they have. And this is sort of a phase diagram, thinking about the early universe way out here when things were dense and hot. And they basically have discovered something they now call the perfect liquid. They've made a kind of a material which has no analog particularly well. And this stuff has amazingly, like, zero viscosity, and it has incredible thermal properties. And they're just trying to learn that. Here's a nuclear and particle physicist trying to learn the language of thermodynamics correctly and trying to figure out what on earth was going on at that time. It's still emerging. This is not a finished story. This is a current story. Now, finally, I want to end with the thing I teased you at the beginning. When they threw away that gigantic accelerator some years ago, here's the airport again in Geneva, Switzerland. You might remember that this laboratory, CERN, is where Dan Brown begins the story of angels and demons here, the antimatter there. In fact, I worked here for 10 years of my life on antiproton physics. So actually, my other specialty besides muons was always low-energy storage of antiprotons. But in this track here, there's a new accelerator coming online called the Large Hadron Collider, and it's going to help answer these sorts of questions about matter and antimatter. This is a different sort of simulation. This one I got from Tim Stelzer, who explains, probably did this simulation. Tim does a lot of these kinds of calculations, and gave a talk on this at one point a few years ago. This is now not so, you don't notice very few things hitting each other. This is a fewer number of billiard balls, but at the extremely high energies. And once in a while, one bit of this proton and one bit of that proton smack so high and so hard that they have the energy to artificially create out of the turning energy into mass, like Einstein said we could do, E equals mc squared. They have enough energy that they can create extremely heavy particles that we've never seen artificially before. And that's what people like Kevin and Tony Liss are trying to do. They are trying to find the Higgs in this kind of debris and other things, supersymmetric particles, whatever the new physics will be that can help explain things like matter and antimatter, why the universe exists the way it is. Here's some interesting facts. You might find this cute, Kevin, because I dug this up on the websites of of the Large Hadron Collider. Suppose how these beams are very high in energy, and the collisions are so, the chance that you'll make something phenomenally new is so rare that you have to have very, very intense beams. So now these things like 30 kilometers around, so imagine how much energy is simply stored in the beam. It's been calculated right here that the total beam energy is this number equal to a British aircraft carrier at 20,000 tons going at 12 knots. That's how much energy is stored in the particle beam. So if you had to like suddenly abort that beam, meaning you couldn't keep it running on its track, there was an emergency or something like that, that is a lot of energy to absorb just to suck it down. And there's some other neat things. There's the TGV train running and so on. It's pretty cool. 7 TeV on 7 TeV, 600 million collisions per second. They have to build some kind of detector which can go that fast, be 600 million events per second they have to be able to deal with. And there's so much energy that when Kevin said it was 1,000 tons for the other calorimeter, this one's got to be way bigger because they could occasionally, the thing they want is going to be so energetic that they have to have a huge detector just to catch that energy and record it once. So what would that look like? Well, here's some pictures of the Atlas detector, the CMS detector. This is some people standing inside the magnet. But this is my favorite one coming up right here. Imagine yourself starting off somewhere in space and having a tour of this experiment. We're zooming in. That's Italy. That's Lake Geneva right there. Right there. This is the size of the experiment, or the accelerator. Here's CERN, the site. Here's me getting very dizzy. The track is underground a few hundred meters. This is the racetrack where the beam goes around. This is the tour. This is the Atlas detector. We're walking inside of it to the very heart where the collisions will occur. Here comes somebody along to inspect it. Now look at the perspective. That's the experiment that Kevin is building. That's why it takes 2,000 people, 14 years to build it. Huge amount of industrial contracts which have to make these things happen. It's 2,000 just the physicists, let alone all of the technicians and everyone else that have to dig all this stuff and go underground. So my conclusion is really this. Watch out for the Time magazine little clip on who's the winners and losers in the next few years, because that instrument will come on in about 2 years. The IceCube experiment in Antarctica is about half built now. In the next couple of years it'll be finished. It's actually operating as it gets built in Antarctica. The RIC accelerator is running right now as we speak, and there's a new beam coming at this underground Super K detector being turned on in about 2 or 3 years itself. So there'll be some new things. Will we find that physics is wrapped up in extra dimensions or supersymmetry? Are there new laws? And frankly, what everybody hopes is there'll be things we don't know. We'll unpeel the onion one more time and find out that somehow nature has been more subtle than we would ever have dreamed. And I think that's because we'll never stop asking the question why, and I'm now very open to any of your questions as to why. This is some read more about it. It's not hard to find the websites here, by the way, of these sorts of things. And it's also nice to know once in a while I get asked about the feedback of this kind of field. What's the give back of this big science? Well, there was the World Wide Web that was emerged out of CERN, grid computing, which is emerging out of the LHC right now, magnets, vacuum, cryogenics, cavities, electronics, thousands of PhDs which go out into industry and drive the economy. So this kind of big science really seeds a lot of things, technical and just the way mankind evolves. Thank you. You can put a link to my talk.
We'll put for the links that Dave had up there. We'll actually put a link to this talk on the Saturday Physics webpage. You can go and
yeah. I mean, I stole like everything you saw there except my work. So
it will be available on the Saturday Physics webpage. We have time for some questions. Please go ahead.
What would be all this? Obviously, a lot of moons in this film all over the world. Or we've accelerated. If you had to sum it up in a couple of sentences, what would be this, is it all MC squared and trying to figure out how energy turns into matter so that maybe we can do that one day? Is that?
No, I would say there's no that phase of so we can do it one day. We know we can do that already. We know we have nuclear power plants and things like that. That's not in doubt. The answer to the question depends on what layer you're asking. So fundamentally, if you're asking physicists that do this kind of work like Kevin or myself or so on, we really want to know. It is driving us crazy whether this standard model that we've had for 30 years, which just predicts everything, is so ugly. It is just hacked together like, you know, a Cub Scout troop that just went out and built their first fort. And you look at it and go, I'm proud you built it, but, you know, it's not going to be on our neighborhood as the house of the week, you know. And so it works. You know, it keeps the rain out, keeps people warm and all that stuff. But something's deeply wrong with the way the standard model's built. And we have to find out. That drives us. We want to know what is the physics that we didn't get yet. So it's a large number of people, a huge part of the community believes there's sort of supersymmetry, which I believe is shown in one of these, like this little cartoon here. And, how much do we believe that? Well, Scott Willenbrock, a theorist in high-energy physics in our department, is giving an entire physics graduate course on supersymmetry. This isn't even proven at all. There's no experimental evidence of this theory at all, but it's so ingrained in our belief that such a thing is important that all over the country people even take courses in it. Imagine taking courses in a theory that has no proof. Same with things like extra dimensions and so on. So we're kind of after, on our layer, we're really after sort of resolving what's been frustrating to us. If you step back a little bit and start thinking about the practical spin-offs of these kinds of machines, well, there's proton therapy, there's lots of cancer treatments from all of these machines, hospitals have these proton accelerators. So they proliferate now into industry, not the giant ones, but the precursors to the giant ones are so standard to build right now that you can build them cheap enough, well enough, in direct beams like into a tumor, which is maybe deeply set inside that you couldn't get with radiation very well, or soft beams that can get on the surfaces of eyes and so on. So the laboratory where I work, this Paul Scher Institute in Switzerland, they have a huge medical facility. Medical patients are coming all the time. And so we just start to see that emerging at all of these laboratories, stuff like that. The computing power to do this Large Hadron Collider was recognized very early on that it would be enormous. So the idea of so-called grid computing means the computing is actually spread out around the world. They've built enormous trunk lines, if you want. Think of it as a trunk line to shoot huge amounts of data to different locations, some to the United States and various places in Europe and Japan. And there centers have emerged. And grid computing means that you're using lots and lots of computers and you're distributing the analysis of the data to many, many places. Our own people here at Illinois, with this other experiment, the one at RIC, the plasma experiment, similarly makes a huge amount of data, because you could see in those pictures that's a lot of stuff in those events. They actually set the world record sending data from New York in a sustained transfer to Japan at some few hundred megabytes a second for, I don't know, a month or 2 months until the whole data set was there. It was a world record. It was written up. And so the computing people are very much taking notice and very much part of this whole thing. And I think that just is going to solve lots of problems. We're going to be able to do the weather, and we're going to be able to do all kinds of other things if we learn how to do that. These things drive that.
Will this CERN situation create any of the conditions necessary for any direct testing of string theory?
That's the million-dollar question, because the more we seem to learn about string theory is that it's less predictive than we would like. So, in fact, there are places, even in this relativistic heavy ion collider thing, that there's a connection between the physics that we think we're finding and string models, for sure. But these connections, if you're a believer, you see it. If you're a doubter, you can ignore it. And I think very indirectly we could get some information on it. Same with extra dimensions as well. So, for example, I'll give you one story I know in this area of extra dimensions, which completely confuses me, right? I could deal with the number of dimensions I'm in, but to add 10, I don't know how. But in this experiment that I do with the little wiggles, in the case of a supersymmetric world where there's supersymmetric particles, they predict exactly what we're getting right now. We get a deviation from the theory. It's exactly predicted numerically by supersymmetry. Fine. If you instead believe that there's a world with extra dimensions, they believe exactly nothing. So that would give no effect on our experiment. So here's our little experiment. It sees an effect or not. It votes for supersymmetry or votes for extra dimensions. These are indirect things. Now, you've got to put a cluster of these kinds of things together. Like, suppose you're in CSI, and you're putting these little clues together. No one single clue is going to nail this. So it's got to be a whole lot of different things that sort of add up to a story. And string theory myself, I'm just very, very non-sure about anything definitive coming out of the predictive power of that yet. Ollie?
I was wondering, with the super K, is it entirely filled with water?
Yes.
Or only about,
No, all the way up to the top. That was what you saw was they were filling it when the guys were on the boat. So it takes a long, long time to fill. It has to be very clean, very pure water, and so on. So it takes a long time. Good question.
There are 2,000 physicists working on a project. Who gets the Nobel Prize?
That is an extremely good question. You are see that guy right there? This one. Let's hope it's Kevin. But it won't be Kevin. In fact, the whole idea of prizes, I was asked this question, interestingly enough, in Indiana, a very similar question. They said to me, even on our little experiment, they say, we've got some real press. Who in that experiment even should get a prize for that? And the answer is already, there's at least 10 people that were kind of equally senior people that pushed that experiment. There were maybe 60 people in the paper. There's probably 10 of us that were pushers of the experiment. So the answer is none. None of us will nominate anyone. And when the top quark was discovered, I mean, maybe that is or isn't the Nobel Prize, but it's at least some kind of a prize. If not the Nobel Prize, it's some kind of a prize in physics. Who's going to get that? The whole batch of you did that. And so what do you think about that?
Well, not only that, so in the case of the discovery of the top quark, at that time, I think our experiment was at about 500 people in size. But in fact, if you think of that's just the collaboration that built the detector. You don't make any top quarks without the accelerator.
Right,
So
right.
add another 500 people who actually built the accelerator and actually made the accelerator. Then you say, who's responsible for this discovery? And there's no way to slice it and dice it. There's no one Einstein who came along and said, there's the top quark. And so the answer is that maybe in the future they would give the prize to a collaboration or a collaborative effort or something like that.
Yeah. That would have to be rewriting of the rules, because the way it's written, it can be given to no more than 3 people, I guess. And so, in fact, when you're in our business, I get asked a lot, you must get even much more, aren't you going to win the Nobel Prize or whatever? And the answer is, we don't even think about that in our business, because it's just not applicable. A theorist like Paul Goldbart could do it. He could come up and tell you, he could write down an equation and say, okay, you guys all need to look at this, and then you'll find, the gold under the rainbow. And then, 2,000 of us will run over there, look under the rainbow. Sure enough, there's the gold. He gets the prize. That's fair. But we're not going to get it. But you better share it. Go ahead.
When you design experiments that create conditions that haven't existed on the Earth before, what kind of guidelines do you use to make sure you don't blow it up?
Okay, that was this thing of people got nervous especially when they were hitting these gold on gold, because they realized all of the advertisement of this experiment for the public was always, we're creating the conditions at the Big Bang. That's what the physicists are saying, it's just to get money. We know how much energy is involved in smacking 2 lead atoms together, just about nothing. I mean, you can't do anything with that. But we're writing down all these popular talks and saying we're creating the Big Bang, something like that. And then people started going, wait a minute, you're creating the what? So that got people pretty nervous. So some serious physicists wrote some serious articles showing it by magnitude, you weren't anywhere close to anything dangerous by this kind of stuff. It was our own undoing for our own advertisement, I would say. It's definitely just no energy at all, what you're used to.
What I mean is, conditions aren't necessarily just the energies that you put into it.
It-
It's part of the Earth. So if you create, for example, eventually as you don't know, that it wasn't known that neutrinos had mass.
Yeah. But we knew the limit, though. We knew it was. It's not like they suddenly are heavy. We just couldn't measure neutrino masses down to some level. We now know they have to have mass, and we still don't know what it is. By the way, we know it's so wicked small, but it's not zero. That's kind of it. What's that? Well, I think we have enough guidance. No experiment has gone to like one, some new kind of a space that we're not close to, where everything is sort of iterative, and we've bracketed enough of this stuff that it's basically not an issue that there would be anything. The kind of physics we're looking for wouldn't suddenly reveal itself as a dangerous thing. The danger isn't that. I could answer your question a different way. There are big dangers in this. It isn't going to be in hitting these things. The big dangers are you have beam and you can make just conventional radioactive mess if you lost that, if you don't shield it correctly, if you let those beams out into the, hit some unshielded area where people live or something like that, that could be pretty dangerous, just like an unshielded nuclear power plant. The highest energy beams the highest intensity beams they're talking about in the world, so-called muon factories, muon collider factories, or neutrino factories, really. They're talking about so many neutrinos that you don't want to be in the way of the neutrino beam. Now that's getting kind of nervous because you can't shield that. I told you how hard it is to shield that, right? So you now don't want to create something like that. That's the danger. It's not that we'll find a piece of physics that'll blow us up. It's rather that we're getting, that you have to be extremely careful with conventional safety, radioactive safety, things like that. That's serious business. Shoot. Yep.
What standard rhetoric has developed out of the physics community or communities to convince governments to spend resources to support all of this? I know in Texas they're going to do something about CERN, and of course that is
Right.
But it is an enormous amount of resources.
It is.
What sort of, other than your curiosity, is used to make
I tried to mention a few things. For example, depending on the particular congressional staffer or so that you're addressing, you could answer with answers that go like this. Suppose that person does not really care about science, fundamentally. Then you can go through an exhaustive list of these sorts of technological givebacks. So let me try that one out on you. Let me assume that you're one of these people that really doesn't care what about the science. If this country is going to sustain a leading role in the global economy, if this country, the United States, is going to do that right now, we are desperately falling behind Japan, China, Europe, Korea, who are investing in their scientists and their scientific programs because they realize, when Japan's economy went down, they poured money into science. So these machines, these Super K, these new particle accelerators, of which there are several in Japan, multi-billion-dollar thing. They're pouring the money into that because what the spin-offs of that in the technical workforce, and just the sort of attitude of the people, is technological forefront, and an economy which is driven by technology is going to lead the world in a way. And if we in the United States sit back and get out of the game, we're just going to be a society that sinks. So I think you can make a better argument than I just did quickly there on the economic power of having a well-trained workforce. So when we're training undergraduates who get a bachelor's degree in physics, who don't go and look at the supersymmetry, but just get out there and start helping, and they become engineers or they work in some kind of a creative workforce, that is vital to this country's survival. My deep, deep feeling is.
So the argument sort of is the answer to fundamental technical workforce is a spin-off in answering those questions, because otherwise you wouldn't bother to train
When I'm up there I'm teaching experimental modern physics right now. I showed you a little flash of a device. We have about 6, 7 pretty cool experiments that are seen. I would challenge that almost nowhere in the country, besides Illinois, MIT, and a few places, can students close to real research, at that level. Now, whether Kevin and I have a great fun finding supersymmetry or not, there's be a limited number of people that buy into that as well. That's like great paintings, art, and orchestras, and so on. I mean, There's the world of science is up there in that sense, just with what always has driven mankind. You can go back thousands of years, and there were scientists and artists and architects and so on. But that doesn't get you a check. You can write a symphony for free, but you can't do this for free. So that would be my approach.
In fact, it's exactly that argument that's behind the so-called American competitiveness.
Yeah.
A competitiveness initiative, which was to increase funding for all the physical sciences, not just for high energy physics.
Double
it over the next 10 years. It was to basically train the next generation to bring the United States up in terms of world competitiveness in science and technology. And that was exactly it started with the Rising Above the Gathering Storm report, which
Right.
was a National Academy of Sciences study that said we're falling behind in math and science and technology and engineering, and what we need to do is train the next generation. And the motivation then for the American Competitiveness Initiative was to put more money into the research and development through universities and through laboratories. So that's exactly the argument that at least the government seems to like. We're running a little late on time.
Yeah,
So
sorry I took so
would
long.
encourage you